Okay, let's look at some other ways of how to measure energy in reactions in this video. Specifically, if you look at the context of colorimetry that we've been talking about. So, in the previous video, we talked about colorimetry. Is one of the things that people do, especially coffee cup colorimeter that can be used to measure the temperature of water change. So using water as a reagent for you to be able to capture how much energy is either released or absorbed, and yeah, from there you can calculate how many joules of energy was either released or absorbed by water. That can also lead into enthalpy change. So how much chemical energy is stored in chemicals that's present before and, well, either before or, sorry, I should talk about delta H, so it's the change from reactant to product. Bomb colorimeter is also another thing that can be used, not very easy for school laboratory settings, because it requires a stainless container that in which mini explosion occurs. But in that, with the explosion, that stainless container need to be kept nice and solid, and it doesn't actually explode. Because the volume doesn't change, all the energy that was released from the explosion will heat up the water that's surrounding the container. So in that diagram, that's the blue part of it. So if you have got water around, same thing as coffee cup colorimeter, you can measure the temperature change while you're stirring, so that you can have homogeneous, I guess, mixture, and the particles which have got higher energy can be dispersed throughout the solution or the water that you are heating up. If temperature of water increases, what that mean? Well, that means the reaction that was occurring inside of water or in the chamber of the bomb colorimeter was exothermic, because energy was released to the surrounding, which is water. Or, well, if the temperature was decreasing, what it means is that it absorbed heat energy from the water, so you would observe the temperature going down. So that's endothermic reaction. The heat released or absorbed can be calculated now for you to determine the amount of heat the heat a substance produces or absorbed. We use this formula of Q equals M times by C, Cp, so heat capacity of water times by delta T, where Q is the heat energy released or absorbed in joules usually. This number itself it is a modulus, so it doesn't have positive or negative value to it. Okay, so you can calculate from that point how much energy was moved from one way or another. So in your answer, you have to say either, say 500 joules was released or 500 joules was absorbed. M is the mass of water. So continuing on with the colorimeter that we were talking about before, we are still dealing with mass of water, and that's the reagent that absorbs or releases heat. Cp is a specific heat capacity of water. Unit is in joules per gram per degree Celsius. It's not in kilojoules, it's in joules. That's another thing that you need to be careful of. That's probably why you get Q in joules. Okay. So this number, heat capacity of water, tells you that how many joules of energy is required if you are to increase the temperature of water, which is 1 gram. Okay, so for 1 gram of water to be heated up by 1 degree, how many joules would you need? That's what CP tells you. Delta T is a temperature change in water. Now, if you consider all those units and put it into where those letters are, that should make sense. So here is what it's showing there. So joules is what you want to find out. That's a Q. M is G. Delta T is degrees Celsius. And C is joules per grams per degree Celsius. As you can see, joules is the only thing that's left, and the grams and degrees Celsius, they all can be cancelled out after doing this calculation. So that's maybe one way of memorizing or how to use or what you're doing. So work with the units. Now, the heat capacity, the C or CP, is given if the substance absorbing heat is not water. What I'm saying is water has got specific number, so it's a constant. It's going to constantly require 4.18 joules per gram per degree Celsius. If you are using metal as a reagent to absorb heat, i.e. change the temperature of metal, it would require, hopefully you're thinking, less energy. Because for water, a lot more energy is required compared to metal. Metal is a good conductor of heat, so you would probably see, I don't know, 2 point something joules per grams per degree Celsius over a metal. Here's an example of what you can do with this formula that I just introduced. So when 12 grams of food was burned in a calorimeter, some sort of a calorimeter, the 100 mils of water in calorimeter changed from 20 degrees Celsius to 33 degrees Celsius. Calculate the heat released. Okay, so you'd go ahead and write down the formula. Q equals Cm delta T. C is 4.18. M, in this case, is a mass of water. 100 milliliters is an interchangeable to 100 grams, so you put 100 grams there. I already did delta T, so temperature change from, so you just have to do a subtraction from the final temperature, take the beginning temperature, starting temperature. If you calculate that, you would probably get 5.4 kilojoules. All right, so I've done that in kilojoules. If you're working with joules, you might get 5,400 joules. And notice that then I've put the word released, because 5.4 kilojoules doesn't have any direction which way it was moving to, because food was burning. It's a combustion sort of reaction, so you need to mention, you need to specify the heat was released. That's for Q, finding heat. Moving on to enthalpy change. Now remember, when you are dissolving, say, sodium chloride into water, well, it would have decreased its temperature. Now, if you're working with heat, but if you are more interested in how many joules would be released or decreased in terms of by knowing, and I'll start again. Delta H would tell you the molar enthalpy change. So per mole, how many joules, how many kilojoules of heat have been either absorbed or produced, released. So enthalpy of combustion or solution or neutralization can be calculated with this formula. So delta H, which in this case is kilojoules per mole. So heat released or absorbed per mole of the substance you used. We are still using water because this can be used for calorimetry So mass of water is the same, temperature change of the water is the same, Cp, heat capacity of water, is still the same. But now we are putting over number of substance and times by, let's say 1000 there as well. Delta H is in kilojoules, not joules. That's why you are dividing the whole thing by 1000. And N is a number of moles of substance that was used, either dissolved or burned or neutralized. So that's what I said just then. Dividing by 1000 converts the unit from joules to kilojoules. All the specifications of all the letters, meaning of that there.